So, question 2 on the workshop is a quenching question. We're given some information about methylacrydium chloride in the presence of adenosine monophosphate, and we're given both lifetime and intensity information, and asked whether the type of quenching is static or dynamic or both, and you're asked to determine the quenching constants in each case. Before that, though, the question asked a little bit about more general kind of bookwork, I suppose. What is static quenching and what is dynamic quenching? So I'm going to just start off with static. So static quenching is where I basically have my excited state and I have my quencher, and between them they can form a complex. So I'm just calling this AQ. This state is emissive and this state is non-emissive. And so the bigger the equilibrium constant, K, and I'm going to call that big KQ, the less emission I see out of my dye. In this case, I only see an effect on my quantum yield and my intensity of my light, and it is equal to 1 plus big KQ concentration of my quencher. I can fit this to Y equals wrong way around, C plus mx. If I instead go for dynamic quenching, in this case I have my excited state and I have my quencher, and I have, in this case, a reaction essentially, which leaves me with a ground state molecule, a quencher, and a bit of heat. In this case, this has a rate constant, which I'm going to call lowercase k, if I make this a k that looks like this. And I can say that the quantum yield and the lifetime, and in this case the lifetime is involved and the intensity are all the same, and this is equal to 1 plus lowercase q tau naught concentration of quencher. And again I can fit this to Y equals C plus, and these two together make my mx. So to get what I need to plot, I just need to kind of fill in a few numbers. So I don't want I over I naught, I want I naught over I. So this is going to be just a case of filling in the table. 2.347 and 3.003. And if I do the same thing here for the lifetimes, I will see that these are not going up at the same rate. And so right now, in my head, alarm bells are going. Because if this was purely dynamic quenching, I would say that I naught over I has to equal tau naught over tau. It doesn't, so in this case I know right off that this is static plus dynamic. So now I have something that's a little bit more complicated. But I know that my dynamic depends upon this value here, and my static and dynamic depend upon this value here. So if I take what is essentially static plus dynamic, and essentially they are multiplied together overall, and I divide them by my dynamic term, I get just my static term. And so this is what I've done here in this I naught over I, tau naught over tau. That is just giving me my static contribution. So if I were to plot I naught over I divided by tau naught over tau against the concentration of AMP, I am going to get my big Ks, my static my static equilibrium constant. If I plot just tau naught over tau, that will give me little k q, sorry, I called them kq, didn't I? And this will give me not just this, but it will give me kq tau naught, but I can easily work that out because I know tau naught right from the beginning of the question. So if I actually go and plot these graphs, I can see this first one. This is just I naught over I, and I can see this is really badly curved. So this one is no good. So this is static plus dynamic together. The tau naught over tau is just showing me my dynamic contribution. And from this, I should hopefully be able to just relatively easily work out my rate constant. So I know that kq tau naught is equal to 0.13141 times 10 to the 3. So the times 10 to the 3 is coming from the fact that this is milli. And so now kq is equal to this divided by tau naught, which is, if I've got this right, 4.0 times 10 to the minus 9 per second. Sorry, it should really be written as per molar per second, shouldn't it? Per molar per second. This final graph here is just the static component, and therefore Ks is equal to my gradient. But again, just be careful with my units here. So this is Ks is equal to 0.0769 times 10 to the 3. And so from this, my unit is just per molar. Hope this helps. Just ask if you've got any questions. We'll just say here that I know I've got slightly different values to what I had earlier. When I hand wrote it, it's because my graphs here have been done on Excel, so I've got slightly different values for my gradient than when I drew them by hand, but it doesn't make any difference.